Okay, guys, so we are busy discussing the molecular geometry when we've added a lone pair and replaced that fourth atom with a lone pair in the case of a tetrahedral structure. Now, I want you to notice something. The molecular geometry changed from being tetrahedral to trigonal pyramidal. Now, what is the difference here? Now, trigonal planar means all the atoms are on the same plane. In the case of a pyramidal molecule, you will see that now the central atom is lifted a bit. And why is it lifted a bit? Well, it's because the repulsion between that lone pair electrons and the bonding pairs is stronger than between the bonding pairs. So these repulsions aren't as great as the repulsion between the lone pair there and that pair. And in the case of an ammonia molecule, our bonding angle will actually change to be 107.3 degrees. Now, what happens if we remove another atom and replace it with a lone pair? Now, this is what happens when we have a water molecule, for example. If I draw the Lewis structure for a water molecule, you will recall that the oxygen atom, which is the central atom, has two lone pairs on it, and then it bonds with each of the hydrogens on the other unbonded electrons. So that would be your structure. So that repulsion over there is stronger than that repulsion over there between those pairs, and the weakest one is the repulsion between those two. So what happens in this orientation is that now we have the lone pairs would be the biggest angle between them, and then the angle between the lone pair and the bonding pair over there, and the bonding pairs would have the weakest repulsion between one another. And look at the change in the molecular geometry. The molecular geometry now we say is bent, or we also sometimes call it angular. Okay, it's at an angle. Okay, but the electron geometry, there's still four spaces where we find electrons, is still tetrahedral. So you will say the molecular shape is bent. Okay, but the electron geometry is tetrahedral. Now, for your purposes, it's most important that you identify the molecular geometry. Okay, so let's recall the different molecular geometries we get. Now, this we say is a non-ideal structure. We would like all the electron pairs to repel one another with a similar strength. But the moment you have lone pairs, that doesn't happen anymore. So this is a bent structure. If we replace one of the lone pairs with another atom, this is a trigonal pyramidal structure with one lone pair. If we replace that last lone pair and we replace it with another atom, we get a tetrahedral structure. If we take away one of them, we get a trigonal planar structure. If we take away one of them, we get a linear structure. So those are our five structures that we are going to look at in this section. And we are now going to look at specific examples of each of these different molecular geometries. So our first example in our notes on page 30 is the one we discussed last, which is the water molecule. Now the water molecule, like I said, there's two lone pairs on the central atom. So there's four areas where we find electrons. So in an ideal world, it should have had a tetrahedral structure with an angle of 109.5. But now the repulsion between the lone pairs themselves, the lone pair and the bonding pairs, and the bonding and bonding pairs varies. So what happens now is that that repulsion is the strongest. So the lone pairs will be the furthest away from one another. Then our repulsion between our lone pair and bonding pair will be of intermediate strength, and then the bonding pairs will have the weakest repulsion with one another. So what we find is that this the amount of degrees that the bonding pairs are from one another is 104.5. So remember, tetrahedral was 109.5. But due to the different strength of repulsions, this angle between the bonding pairs is now only 104.5. And we say the structure of the water molecule is a bent structure. So whenever you have four areas, four domains of electrons with two lone pairs which is on the central atom, you will have a bent or an angular structure. Now, this structure, if we look at the bonds, guys, and once again, like I said before, we have to distinguish between the classification of the bonds and the molecule. The bonds in a water molecule is polar covalent due to that electronegativity difference of 1.4. And please look, guys, that we don't calculate the electronegativity difference for the molecule. You calculate it for that single bond there between an oxygen and a hydrogen to classify the bond's polarity. If we look at the molecule, we've said before that a water molecule is polar. It's a dipole. Why? Because you've got that uneven distribution of charge around the oxygen atom, where you've got more electrons than around the hydrogen. So it gets a slightly positive charge around the hydrogen atoms and it gets a negative charge around the oxygen atom. So a water molecule is polar with polar covalent bonds within the molecule. Our next example that we are looking at is all the group 6 hydrides. All the group 6 atoms have 2 lone pairs. So therefore, all of them, if they bonded to hydrogen, will form structures that are bent. Important, guys, these bond angles for hydrogen sulfide won't be 104.5 anymore. It will differ because you've got different atoms. It's only 104.5 for the water molecule. For these others, we don't have the exact bond angles and you don't have to learn them. You don't need to remember or recall them. So just take note that they will be smaller than 109.5, which is the ideal bond angle for 4 areas of electrons, which should have been tetrahedral, but because of the lone pairs, the structure we say is now bent. If we go down to our next example, it's the ammonia molecule, which we've also discussed. On the ammonia molecule, the nitrogen atom has that lone pair of electrons. So instead of having a tetrahedral shape, we say it has a trigonal pyramidal shape, or just a pyramidal shape. And specifically with the ammonia molecule, the bond angle between the hydrogens is now 107.3 degrees. Once again, the repulsion between the lone pair and those the bonding pairs is weaker than the repulsion, or stronger than the repulsion between the bonding pairs themselves. If you look at the polarity of the bonds of a ammonia molecule, it will also be polar covalent, but due to this uneven distribution of electrons, the molecule as such is also polar. Okay, then if we look at all of the group 5 hydrides, all of them, because the central atom has a lone pair of electrons, all of them will have a trigonal pyramidal structure and will be dipoles. If we go to our next example, our methane. Now here we also have 4 areas of electrons, but it's our 4 atom scenario. And all of those are bonding pairs. So their repulsion with respect to one another is exactly of the same strength. So we say this is a tetrahedral shape. And the bond angle for tetrahedral shape is 109.5 degrees. And because it's a tetrahedral shape and you've got similar atoms on the sides, the repulsion will be the same. You will have an equal distribution of charge across the molecule, even though the bonds are polar covalent. So here is our first ascension, where we have a non-polar molecule with polar covalent bonds. So you have an equal distribution of charge across the molecule. They will all pull these electrons towards the carbon with the same strength, and you will have a symmetrical charge distribution, and therefore it's a non-polar molecule. Now, in the case of your group 4 hydrides, you don't have lone pairs on the central atom, and all of them have polar covalent bonds, but the molecule as such is non-polar. polar. Now, before we go on to the questions, guys, I just want to show you an exception on this rule. So let's say we had a molecule CH3Cl. If we draw the Lewis structure of CH3Cl, what will we have? We've got 3 hydrogen carbon bonds, okay? But then we have 1 carbon chlorine bond. Now, all of the bonds will be polar covalent. However, what about the polarity of the molecule? I want you to look at the distribution of these electrons. Chlorine is much more electronegative than any of the others, and it has lone pairs around it. Okay, so in this case, there will be an uneven distribution of charge, and what will happen is that the molecule as such will be polar due to the presence of that chlorine atom. Okay, guys, so basically we can summarize our discussion of molecular geometry as such. Okay, so the molecular geometry is determined by the valence electron pair repulsion, both the bonding pairs and the lone pairs. The theory that we use is called the valence shell electron pair repulsion, FISIPA theory. According to this theory, lone pair repulsions are the greatest, lone pair bonding pair repulsions are of intermediate strength, and bonding pair repulsions are the weakest. Molecules as a whole can be classified as polar or non-polar. Remember now, if you classify bonds, you use electronegativity differences. If you classify molecules as polar or non-polar, you have to look at the molecular geometry and the distribution of electrons. If there are lone pairs on the central atom, that's it. It's a polar molecule. If there's no lone pairs on the central atom, you have to look at the other atoms bonded to the central atom, because then it will determine how those electrons are distributed. Okay, polar molecules have an uneven distribution of electrons, an uneven charge density. Non-polar molecules have an even distribution of electrons, an even charge density. Molecular geometry assists us in understanding the polarity of a molecule and its reactivity, how it will react. It also assists us in identifying and explaining the type of forces called intermolecular forces that we find between molecules. Now, according to the FISIPA theory, there are 3 ideal geometries that we need to take note of. There are many more, but we are focusing on these 3. We get the linear molecular geometry, where the bond angle is 180 degrees. And these can either be like our diatomic molecules or our hydrogen halides, or it can be something like CO2. In the case of CO2, even though we've got different atoms bonded to the central atom, they are both attracting those electrons on the central atom with the same strength, and therefore the tug of war remains even. Another example is a trigonal planar structure, where the bond angle between the bonding pairs are 120 degrees. BF3, BH3 are examples here. Then we get our tetrahedral structure, where the bond angle is 109.5 degrees. And an example here is methane. Another example can be something like chloromethane, CH3Cl. But in the case of CH3Cl, where methane is non-polar, CH3Cl will be polar because the chlorine has got lone pairs around it, and therefore there's not an even charge distribution. Our last 2 structures that we discussed were our non-ideal shapes, shapes where we have lone pairs, and because of lone pairs on the central atom, these molecules are always polar. The first one was the bent or angular structure. Here we had group 6 hydrides, and SO2 is another example. The bond angle will be less than 109.5. It has 4 areas of electrons, so it should have been tetrahedral. So that's why it's 109.5 is important, but now the repulsions are different. And in the case of water, for example, the angles between the hydrogens would be 104.5. Our final one is the trigonal pyramidal structure, which has 1 lone pair, and it's also less than 109.5. And our group 15 hydrides is an example.